In this episode, we ease into probability distributions in a way that feels more like learning a new lens for looking at uncertainty than memorizing a pile of formulas. When people first hear the word distribution, they often picture a messy chart and assume it is only for advanced math students. But the core idea is actually simple and practical. A distribution is a structured way to describe how likely different outcomes are, especially when you cannot predict the exact outcome ahead of time. That matters in data and AI work because you are constantly dealing with variation, like differences in user behavior, sensor noise, or the natural randomness in sampling. Once you understand what distributions are saying, you stop treating randomness as chaos and start treating it as information. The goal here is to make you comfortable switching between 3 common ways to describe a distribution and 1 common way to summarize it, so you can interpret questions quickly and avoid classic beginner mistakes. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at Cyber.Author.me in the Bare Metal Study Guide series. A probability distribution is not a single probability, and that distinction is the first misconception to clear up. A single probability answers one question, like what is the chance the coin lands heads, while a distribution answers a family of questions, like how likely is each possible outcome, and how does that likelihood spread across values. You can think of it like a menu versus one menu item. A single probability is one item, and a distribution is the entire menu that tells you what is available and how likely each option is. This matters because many exam questions are really about your ability to move between statements about individual outcomes and statements about the overall behavior of a variable. Another easy trap is confusing the thing you measure with the probability you assign to it. The measured value, like a temperature reading, is not a probability itself, but the distribution is what tells you how plausible different temperature values are in a given context. When you keep these roles separate, the rest of the topic becomes much more intuitive. To talk about distributions clearly, you also need to be comfortable with the idea of a random variable, which is just a label for an outcome that can change. The word random does not mean meaningless. It means we are acknowledging uncertainty in advance. A random variable can be discrete, like the number of failed logins in an hour, where the possible outcomes are countable numbers. A random variable can also be continuous, like the time it takes for a model to respond, where there are infinitely many possible values in a range. That discrete versus continuous split is not just vocabulary, because it determines how probabilities are represented and how you interpret graphs. Beginners sometimes try to use the same logic in both worlds, like expecting a single exact continuous value to have a non-zero probability, and that causes confusion. Once you treat discrete outcomes as countable and continuous outcomes as spread out, the different tools will make sense. For discrete random variables, one of the most common representations is the probability mass function, PMF, and the word mass is a hint that probability is placed directly on specific outcomes. If a variable can take values like 0, 1, 2, or 3, then a PMF assigns a probability to each of those values, and those probabilities add up to 1. Conceptually, you can imagine the probability as little chunks sitting on each allowed outcome. If you ask the probability that the variable equals 2, you can point to the chunk at 2 and read it directly. The clarity of a PMF is why it is so useful for counts and categories. A typical beginner mistake is forgetting that outcomes not allowed by the variable have probability 0, which sounds obvious until you see someone accidentally assign probability to an impossible value. Another mistake is assigning probabilities that do not sum to 1, which breaks the whole idea of a complete description of uncertainty. For continuous random variables, the probability density function, PDF, plays a role that looks similar at first but works differently in an important way. In a continuous setting, probability is not assigned to single exact values. Instead, probability is spread across ranges of values. A PDF tells you how dense the probability is around each value, like a landscape where higher hills mean outcomes in that neighborhood are more likely than outcomes in a lower valley. The key is that the height of a PDF at a point is not itself the probability of landing exactly on that point. Instead, You get probabilities by taking an area under the curve over a range. This is where many beginners get tripped up because they see a high peak and assume it means a high probability for one precise value. The better interpretation is that a high peak indicates many likely values clustered nearby, not a single value with a big probability attached to it. Keeping that area idea in mind prevents a lot of confusion. To connect the discrete and continuous worlds, it helps to see what stays the same and what changes. In both cases, you are describing uncertainty about a variable, and you are still using the idea that total probability must equal 1. For a PMF, total probability equals 1 by adding the chunks across outcomes. For a PDF, total probability equals 1 by taking the entire area under the curve across all possible values. Another common similarity is how you find probabilities for a range. With a discrete variable, you add the probabilities of each allowed value in the range, and with a continuous variable, you take the area under the curve over the range. The difference is that the continuous range contains infinitely many values, so the area idea replaces the chunk idea. When you practice interpreting questions, the first thing you should decide is whether the variable is discrete or continuous, because that tells you whether you will be thinking in terms of sums or areas. This single decision often eliminates wrong answer choices quickly. Now we move to a representation that works smoothly for both discrete and continuous variables, the cumulative distribution function, CDF. Instead of telling you the likelihood of each exact outcome or the density at each point, the CDF tells you the probability that the variable is less than or equal to a given value. That sounds like a small change, but it is incredibly powerful because many real questions are naturally phrased as thresholds. For example, you might want the chance that response time is below a service target or the chance that the number of errors stays under a tolerance. The CDF answers that kind of question directly. Another advantage is that the CDF is always non-decreasing as you move to the right, because as the threshold increases, you include more possible outcomes. Beginners sometimes confuse the CDF with the PDF because both can be drawn as curves, but the shape behavior gives it away. The CDF climbs and eventually approaches 1, while a PDF can rise and fall like a hill. There is also a practical relationship between these representations that can help you translate quickly in your head. For a discrete variable, the CDF at a value is the sum of the PMF probabilities up to that value. For a continuous variable, the CDF at a value is the area under the PDF curve up to that value. This means that a CDF is essentially an accumulated probability, and accumulated probability is often easier to reason about in threshold problems. If you want the probability that a value is greater than a threshold, you can use the CDF by remembering that the probability of being above is 1 minus the probability of being at or below. That simple complement idea shows up constantly on exams because it tests whether you can reason without getting lost in details. Many learners try to memorize special cases instead of building this one flexible habit. Once you understand CDF thinking, you can answer a wide variety of questions without new memorization. Expectations are where distributions start to feel like they are giving you usable summaries rather than just pictures of uncertainty. The expectation, often called the expected value, is the long-run average outcome you would get if you repeated the process many times. It is not a promise of what happens on one trial, and it is not always the most common outcome, which is another classic misconception. If you have a distribution that sometimes gives a large value with small probability, that rare event can pull the expected value upward, even if most outcomes are smaller. This matters because in real systems, rare events like spikes in demand, bursts of errors, or unusual user actions can have outsized impact. In a discrete case, you compute expectation by multiplying each outcome by its probability and adding those products. In a continuous case, the idea is similar, but you use a weighted average across values using density, which is why you often hear expectation described as an average that accounts for likelihood. The mental model to keep is that expectation is a balance point for the distribution. It also helps to distinguish expectation from other summary ideas you may have heard, like the median or the mode, because exam questions sometimes test whether you know what each one means. The expected value is sensitive to extreme outcomes because it accounts for magnitude as well as probability. The median is the value where the CDF reaches 0.5, meaning half the outcomes fall below and half fall above, and it is less sensitive to extremes. The mode is the most likely outcome in a discrete distribution or the highest point of density in a continuous distribution, and it tells you where outcomes cluster most strongly. If a distribution is symmetric and not heavy-tailed, these values can be close, but in skewed distributions they can differ significantly. Beginners often assume they are always the same because they have only seen nice bell-shaped examples. In applied work, and on exams that reflect applied thinking, the differences matter. Understanding these differences is part of interpreting what a distribution is really telling you about risk and typical behavior. Let's walk through a simple discrete example in words, because it builds intuition without needing you to do long math. Imagine a system where the number of alerts in a minute is usually low, but occasionally spikes, and the possible outcomes are 0, 1, 2, 3, and 4. A PMF might show that 0 and 1 are most likely, 2 is less likely, and 4 is rare. The CDF would start near 0 and climb as you include 0, then 1, then 2, and so on, and you could answer questions like the chance of having at most 2 alerts by looking at the CDF at 2. The expectation would be the average alert count over many minutes, and it might be closer to 1 than to 0, even if 0 is the most likely single outcome, because the higher outcomes contribute more weight when they occur. The important lesson is that each representation answers a different kind of question quickly. When you see which question is being asked, you know whether you want a point probability, a threshold probability, or a long-run average. Now consider a continuous example in plain language, like response time in seconds for a service. You might have a PDF that is low at very small times, rises to a peak around a typical time, and then trails off to the right where slower responses live. If you want the probability that response time is under a target, you use the CDF at that target because it captures the area under the curve up to that point. If you want the probability that response time falls between two values, you take the area between them, which is the difference between the CDF at the upper and the CDF at the lower. The expected response time is the weighted average, which can be pulled upward by occasional slow responses, even if most responses cluster near the peak. A beginner trap here is thinking that the highest point on the PDF curve is the probability of that exact response time. But the correct view is that it is the density, and probability is area across a range. Another trap is forgetting that probability must live between 0 and 1, while density values can be greater than 1 in some situations depending on units and scale. These details sound small, but they are exactly the kinds of misunderstandings exams like to probe. As you practice these ideas, you will notice that many questions are really asking you to translate a statement into the right representation. If the question asks for the probability of an exact discrete outcome, you are in PMF territory. If the question asks for the probability of being below, above, or between thresholds, you are in CDF territory, whether the variable is discrete or continuous. If the question is about what value you should expect on average, you are in expectation territory. If the question involves continuous ranges and mentions density or areas, you are in PDF territory. Building this translation habit saves time because you stop trying to force every question into the same pattern. It also helps you avoid mixing rules, like adding densities as if they were probabilities or interpreting a CDF value like a density height. The exam will often present choices that reflect these common mix-ups, and your job is to choose the option that respects the correct meaning. When you keep the roles clear, your reasoning stays stable even when the wording is tricky. To wrap everything together, probability distributions are the language we use to talk about uncertain outcomes in a structured, testable way, and learning that language gives you control over problems that initially feel abstract. You learn that a PMF assigns probabilities directly to discrete outcomes, while a PDF describes how probability is spread across continuous values through density and area. You also learn that a CDF is the accumulated probability up to a threshold, which makes it ideal for answering many practical questions quickly. Finally, you learn that expectation is a weighted long-run average, useful for summarizing a distribution, but easy to misinterpret if you treat it like a guaranteed outcome or the most likely outcome. If you can recognize whether a variable is discrete or continuous, choose the right representation for the question, and interpret that representation correctly, You have built a foundation that will support many later topics in data AI, including hypothesis testing, regression, and classification metrics. That foundation is not about memorizing math tricks. It is about understanding what each tool means and what kinds of questions it is designed to answer. With that understanding in place, probability stops feeling like a fog and starts feeling like a clear set of ideas you can use confidently.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.